Okay, good afternoon, everyone. Welcome to this third webinar, GRAPHIA webinar, which is an introduction to large language models through GRAPHIA. My name is Matteo Romanello. I'm the Research and Development Lead Project Manager at Odoma, which is a small and medium enterprise in Switzerland developing AI-driven solutions for the cultural heritage. In GRAPHIA, I'm coordinating work package 4, which focuses on large language models for the social sciences and humanities. So if you are in this webinar, it's fairly likely that whether you know it or not, you have already encountered LLMs. They are present in our lives and they work in many different ways. As conversational interfaces, like Claude, ChatGPT, and Gemini, as AI-powered tools for coding and vibe coding, like Cursor or Replit, or even like for deep research, like Perplexity. Or again, you may have written some code to download one of these models from Hugging Face and make calls to it via the API in a notebook. So especially if you find yourself in cases 1 or 2, experiencing these models via graphical interfaces can have the effect of hiding, for the good and for the bad, the technical details of what happens behind the scenes when we use these models. At this point, also to get to know a bit you as an audience, I'm gonna try to launch a poll, which I hope you see. The very simple question. If you're joining in this very minute, there is a poll going on. How familiar are you with large language models such as ChatGPT or Claude? And then we see a bit what is the audience we have here. We are missing 6 people on this one. Do you see also the results of the poll in the Zoom?
Yes.
Okay.
I can see them.
Okay, so there is no need to share them. Yeah, so I think we can stop here. So we have.
Actually, we cannot.
Yes, we don't see the result.
Okay, I
So
need to end the
you
poll.
need to share. Okay.
Okay, yeah, I will end the poll. So last call for the poll. With three people missing, but it's not a big deal. We can end it here. Maybe I need to share the results. Yeah, so 67% who use them regularly in their work or studies, 20% who use them occasionally, 10%, 11% having tried them a few times, but not using them regularly, and a small percentage of I'm not familiar with them at all. I have another one for you. This is great, super helpful. Let's do another quick one. Should be launched now. So, which is more about the how. How do you interact with LLMs? How do you most often interact with large language models? The poll is launched and answers are coming in. So either you do it through conversational interfaces or through AI-powered applications programmatically, through tools integrated in software that you use, or people who are not sure or don't use LLMs yet, which is probably going to be like the same 2% from before. We are almost there, 94%, 96, 2 missing, and then we are done. I think I'm going to end it here and share the results. The results are also interesting. We have 92%, so the vast majority, using them via conversational interfaces, 35% through AI-powered applications, a fourth using them via APIs or notebooks, and then 22% through tools integrated in software I already use, and the same 2%, I guess, who is not familiar with them. So welcome to all of you, independently from your level of kind of familiarity. Also, if you are more advanced, I hope this introductory webinar is still useful. So to go back to my slides, the objectives for today's webinar on my side, there are three. So the first one, as I was saying before, graphical conversational interfaces tend to hide a bit the details of how these models work. So first objective is try to bring that to the surface. Second objective is to get more familiar with LLMs, understand a bit the inner workings, the limitations, and unpack a bit the jargon, which is quite frequent when we talk about LLMs. And then in the second part of the webinar, I'm gonna let you discover and explore a bit what we are doing in Graphia when it comes to adapting large language models to the SSH domain, and also when it comes to serving and deploying models for our partners and community. So let's start with the introductory part. And before getting into things, I really wanted to define a bit what is the perimeter, of today's webinar. First of all, I'll be talking about generative models, which now we use LLMs as a shortcut to call them. But there are many other types of LLMs out there that are also non-generative. So they will not be covered and they will not be focused of today's webinar. The second point is that I will focus mostly on the GPT architecture, but there are out there many other LLM architectures that we will not be touching upon or covering. And the third thing is that although when you interact with LLMs, you mostly do it via text, these models are now largely multimodal with vision language models and so on becoming very popular. And they will also not be covered in this presentation. So that's a bit, for me, the perimeter for today. So the name ChatGPT has entered so much our lives that we often use it without knowing what the acronym means. But this acronym nicely summarizes the main ingredients of an LLM. So the G stands for generative. A GPT is a model that has been trained to generate text in a way that mimics the human production. It generates text in several languages, knows about and can use different styles, different tones in the text it produces. The P stands for pre-trained. It is a model that has been trained with massive quantities of data and using very powerful hardware, the graphical processing units or GPUs. And finally, the T stands for transformer, which is the model architecture used in LLMs, which has a very sophisticated way to model and capture the relations between words, context, and emotions that get expressed in the text. So a core concept in machine learning is the one of model training. In a nutshell, during the training, a model learns how to perform a task based on some pre-existing data that are usually annotated by hand. Up until 4 or 5 years ago, the kind of dominating model training paradigm consisted in training a new model for each new task. The resulting model will perform well a task in a given domain, but will not perform well on a different domain. Or a bit more technically and precisely, it will have problems to generalize. So for example, if your model is trained on extracting names of people and places from legal text, if you try to do the same from scholarly publications, it might underperform because it's not able to generalize to a new domain. Now, this with LLMs, this paradigm has changed deeply, because we now talk about LLMs as foundational models that don't need to be trained on specific tasks, but they are already pre-trained on massive quantities of text, and therefore they have such a knowledge that they can be steered and told to perform different tasks on which they have not been trained without retraining the model just by telling them to do so. And we'll see an example later on. There are two ingredients to the pre-training. The first one is data, and especially a lot of data. So here there is a static version, but I'll recommend to check out also the interactive version of this chart, where you can explore it interactively and see the different sizes of models. But basically, there has been a linear trend in the increase in the size of the data sets that are used for training these models, to the point that now we are training on hundreds of trillions of words, corpora that have hundreds of trillions of words. So really large corpora to train these models, with many consequences that I'm not going to discuss right now. And then the second ingredient is the computing. Training this type of models is not something you can do on most of the time, especially for the larger frontier models. You cannot do it on your consumer hardware, but you will need supercomputers, AI factories, and the like, with hundreds or thousands of GPUs, where these models can be trained over several days. But what is to go a bit more into detail, what is the task used during the pre-training? Well, the task, it's actually very simple, and it's a task of filling gaps or predicting the next word in a sequence. And the principle is quite simple indeed. You take a very large corpus of documents and chunk up each document into chunks of a given size. Here, for the sake of the example in this slide and the following, we can assume that our chunk corresponds to a sentence, but in reality, they are bigger, and this can also vary. So we work with the input sample sentence, the historian studies archives. There are two different variations of this task. One is called masked language modeling, where basically you hide one of the words in the input text, and then the task that the model has to perform is to guess what is the word that has been hidden by looking at the right and left context of the masked word. So in this case, it's the historian archives, and we'll have to guess that the verb implied here is studies archives. We can also have another case where there is a different word that is masked, and the answer that the model gives is actually not the correct one. So in this case, researcher would be synonym or closer to historian, but actually not the word in the text. And the second example type of this type of pre-training is the next token prediction, where you start from the beginning of the sentence with the first word, and at each step, the model has to predict which is the model that comes after. So we start with the historian, and then we gradually go until the end, including punctuation if there is any. So you may wonder, what is that makes this task so powerful? Well, mostly is the fact that it doesn't require any supervision, meaning any human annotation. It's a so-called self-supervised learning approach. Is simply, if you can have it, can provide it, requires a large enough of corpus of text so that this task can be repeated millions and billions of times over and over again. The second element of the acronym, so here, as you might have seen, I'm following the, not in the right order, but the generative pre-trained transformer, so the 3 letters in the acronym. The second letter is indeed transformers. And transformers are a topic that in itself could be the subject of probably a week of learning, not just one webinar. So I don't have the ambition here to explain kind of the nitty-gritty details about the transformer architecture, also because I'm not the best person to do that. But what I would really like to give you is more like an intuition of the type of model that is used in LLMs. And this intuition has three elements. So the first element is that you have to imagine a transformer as a multi-layer network. So a network made of connections, of course, because it's a network, and of many layers of increasing complexity. And also think of this layered network as something where each layer transforms or enriches the representation that the model has of the world. For now, I have introduced the term token. I will do it in a few slides. When you see token, you can think of word simply. So that's a multi-layer network. The second element of the intuition is that it's a network made of billions of parameters that are also called weights. And a good kind of mental model for this is to think of these parameters as a very big panel made of dial knobs that you can turn and tune in different ways. And all these knobs, all these parameters capture different linguistic patterns between the words in the language. Third element of the intuition is the attention mechanism, which is basically the ability of the model to weigh the relationships between all words in a sequence. So if you look at the image on the right here, and going back to the example that I had in the previous slide, there will be a stronger link between, for example, historian and studies, because historian is the subject of studies. So it's a mechanism that allows the model to model and represent relationships between all words in a sequence. By the way, this illustration is taken from the illustrated guide to transformer, which, if you're interested to dive into this topic, is a great starting point, although it does get quite technical. So let's now dig a bit into what is the actual training process. So the first step is to tokenize the text. So if you used LLMs before, you probably come across the word tokens, which is usually which is the way in which we pay. So it's how the pricing of LLMs is computed. You pay by token consumed by the model, by token in input, and also you pay by token produced by outputs. Tokens, what they are, they can correspond to words, but they are often these LLMs use subword tokens.
Yeah, it's not mommy.
Can you just mute yourself, whoever you are? Thank you. Often these LLMs use subword tokens, which capture, for example, prefixes and suffixes. And this allows to reduce the number of tokens necessary to represent the words in a large corpus, given that subword tokens are reused across multiple words. One thing to highlight here is that tokens, so if you take your sentence, the historian studies archives, is chunked into tokens, which in this case, they also corresponds to words, and then they are converted in the model's vocabulary into token IDs. The model never sees words, but it always manipulates token IDs and numerical representations of these IDs. The second step is to transform each token indeed into a numerical representation of it. So each token is associated to a numerical representation, which is called vector, that captures its meaning. Similar tokens will be characterized by similar vectors. And given that this representation is numerical, the similarity between two tokens, two words, can be measured as the distance between their vectors. At the very beginning of the training process, all token embeddings are initialized. When I say embedding, it's a synonym for vector. They are initialized with random values. And then they are updated at each of the millions and billions of training iterations. The size of the vector, which is the number of the dimensions it has, can vary. And this depends on the model size, on the model usage, but it's usually somewhere between 300 and 1,000 dimensions. So the model doesn't see words, but sees numbers representing IDs and vectors representing somehow capturing the meaning of the tokens. What happens then in the third step, which is when the transformer processes the context, is that the vector for each token flows through the different layers of the transformer model, and at each step, its vector is transformed and enriched with more context and more meaning. So this is the step in which the model will weigh and capture the relationships between tokens in this sentence. Finally, we get to the last step when, as I showed a few slides before, the model has to predict the next token. So here we have the sequence up to this point of the historian studies, and the task of the model is to predict what comes next. What happens at this stage is that the vector for each token is enriched with more context and meaning, and the representation of each token in the sequence is updated to capture the preceding context and forms what is called a contextual embedding. And this contextual embedding can be thought of as a kind of the compressed meaning of a sentence up to a certain token. So when we get to process the token studies, the contextual embedding of studies also contains the context about all the sequence before that token. And the contextual embedding of studies captures information about what comes before and is then used as a signal to predict the token that comes next. Or, in other words, predict the token means selecting from the model's vocabulary the most likely token to complete this sequence. In this case, the most likely would be archives, but there are other words in there that are competing, like books, history, or records. So what happens at this stage is that then the model compares the predicted answer with the correct one. If they don't match, it computes a loss, which is kind of obscure word to say an error, which quantifies essentially how far is the predicted answer from the correct one. And then the model does what it's called backpropagation. So it goes back and it updates, it tunes in, and it adjusts all the dial knobs in your big panel according to how big the error was. And this includes also the embedding. So what happens at this stage is that the vector representation of each token moves closer to words with similar meaning in the space that the model is using to represent semantics. I will have to skip this slide, but when you get the link, I totally recommend to try it out. So it's an interactive demo where you can actually see, you can type our example in there, and you can see how at each time when you type in there a new word, you get the list of other probable words with their probabilities that the model can choose from. So this to say that the G in generative stands for the fact that LLMs are massive statistical models of language that are trained to generate text by predicting the next token. And here I will switch to the demo, to a little demo. Just to exemplify what we were saying of the fact that the fact that these models are trained to predict what comes next in a sequence. So what I'm gonna do here because I'm lazy, I'm going to do something like this. So to ask the model to extract named entities, so without specifying entities that are mentioned in the text. Maybe I should say where I am here. So you might have noticed we are in the GRAPHIA SSH domain space. So this is what we call our LLM Gateway, where you can authenticate and use, if you're a member of GRAPHIA, the different models that we make available. So let's try to this, and as you see here, is just a more complicated version of what I showed, the example that I showed before, of giving a sentence and having to fill in what comes next. Here, I'm actually asking to do a task of extracting entities from a sample sentence, and we get some sort of an answer. So the model says, person Voltaire, location Ferney, Geneva, provides an explanation of who is Voltaire, what is Ferney, what is Geneva, even though I didn't ask for that. So now to go back to the presentation, what I just showed you here of my question, which in this case it's not really a question, it's more an instruction. In the LLM jargon, is called a prompt, and the prompt can be used to steer the LLM behavior, and can be used also to steer it in a way that it lets the model perform a task for which it hasn't been trained before. So there are some elements of the prompt of this question that allow you to say more in detail what the model should be doing, to instruct it more precisely on what it should be doing. You can provide context for your task. You can tell the model which role to perform. You should tell it what is the action that you want it to do, and then you can also tell what is the output that you want. So all this helps the model to then basically, without having been trained, even if it hasn't been trained on a specific task, to perform it, which is what I meant at the very beginning by the fact that these are foundational models. So to go back to my demo, I can do should probably do kind of a new chat. I can do a slightly more complex example where I'm actually specifying more precisely what is the task that should be doing and what is the output. So here I say identify named entities in the text, use the following tags. So I'm specifying what I want and how I want that to be output, return the output as entity tag pairs. What I can do, it's also to provide some examples. So in this case, I think I'm providing 3 of them. I'm providing 3 examples of sentences with their entities annotated. So Napoleon was defeated at Waterloo in 1815. In Florence, Dante wrote the Divine Comedy during his exile, and so on and so forth. So this will help the model to understand what is the task I'm asking it to do and what is the output that I'm expecting. And if we try this, then we will see that the model doesn't take any initiative, for example, on the output adding information, but it sticks to the instruction that I gave to it. And this type of prompting of adding examples into a prompt, it's also called in-context learning or few-shot prompting, where we teach the model to perform a task for which it hasn't been trained by providing guidance and examples on how to do that. And as you can understand, it's very powerful because this becomes like a programming interface, basically, that we can use to steer the behavior of the model. One word about the limitations and some solutions to these limitations of these LLMs. One limitation that you might have already come across is hallucinations, which is when models are asked to provide an answer that requires some factual knowledge. They don't have access to this knowledge, and then they will hallucinate. So they will provide an answer that it sounds plausible and legit, but it's not actually true. And this is a big topic, but in a nutshell, LLMs are model of languages, they're not model of truth. And more technically, this is also due to two factors. The first one is that these models are trained not to say, I don't know the answer, but they are trained to continue a text. So even if they don't have enough evidence to provide the answer, they will still try to do that. And the second reason is that the knowledge, the factual knowledge you have in these models that comes from the pre-training data, it's frozen at a certain point in time. So this is called like the training data cutoff date. So the date when the data was stopped being collected, meaning that if you ask the model for something that happened today or yesterday, it will not have it. It will not be able to provide an answer and will probably hallucinate. One popular solution to this, which was then is articulated in many different flavors, is the so-called retrieval augmented generation. And before going into the concept, even if you don't know it, you might have already come across it, because nowadays tools like Perplexity or even ChatGPT, they do it by default, or if you ask it to do it. They will provide this sort of footnotes where you, for a given statement, you can see what is the actual source that the model used to arrive at that statement. So this is useful in cases where the information that the model has to find maybe is contained in a very long document, like a book or a file with several books, or when this factual knowledge is not available to the model because of this cutoff date in the pre-training data. So the way that RAG works, and I will only touch upon it, so RAG stands for Retrieval Augmented Generation. So the idea is that instead the model giving the answer purely based on the prompt, it will enrich the prompt with some contextual knowledge that comes from a different source. Here generically called a search database, can be the web, can be your Zotero library, can be your collection of notes in Obsidian, any collection of text that can be used to extract information. And then what the model does, what the RAG application does is goes to the database based on the prompt, retrieves some bits and pieces that relate to the prompt, injects them into the context, and then it updates the prompt. So this updated prompt is then used by the LLM to provide the answer. Again, RAG in itself, it's a topic that one could explore. There are many different variations. There are different implications of doing these different techniques that can be used. So it's in itself a whole topic to explore if you're interested. But the topic of hallucinations brings us also to briefly talk about actually assessing the model's strengths and weaknesses. Why does it matter? But this matters for one main reason, which is that the capability of these models and also the landscape of these models is evolving very rapidly, which means that we need ways to determine how these models are progressing, how much better they can perform the task that I'm interested in. So basically, we have moved to a phase where we need to be doing some kind of continuous benchmarking, so continuous evaluation of all the new models that come out. How is this done? This is done through benchmarks, which are curated test data sets containing basically questions and answers that can be used to test the models and then to assess their performances. And many times these benchmarks are combined into leaderboards that provide rankings of these models with a comparison. One of the issues there is that these benchmarks, they don't cover in a homogeneous way all tasks and domains. And often in the humanities, we are kind of lacking the benchmarks to be able to test these models. And that's here that I want to mention this project by the University of Basel that are putting together a benchmark that can be used to, a benchmark that is specific to the humanities, to tasks like OCR or bibliographic data extraction, and can be used to benchmark existing models against these tasks. This system of evaluating also has some limitations. There is the problem of leakage, so benchmarking being included into the pre-training data so that the model already knows the answers to the questions it's been asked. Model providers often they optimize the models to be performing in this leaderboard, so they kind of tweak a bit this evaluation, and then the problem that I've already mentioned of covering different tasks and domains. Even though there is not really much time to go into this, but I wanted to briefly touch upon LLM agents because they are quite a bit of topic of research right now, and they're also quite interesting. Basically, an agent is when you put the large language model on the driver's seat and you give to it tools and data to perform a certain task. So the main components of an LLM agent are kind of a reasoning engine, which is done by the LLM itself, tools and APIs to do many different things, to search the web, to execute code, to look into databases, a control loop that basically defines the different steps of the agent. So there will be a phase where the agent plans the work to do, the act phase where it will actually do something, for example, write some code, or do kind of literature research, and then to observe the result. For example, it has run some code, it raised some errors and exceptions, it will observe and try to debug it. And then this control loop, basically, it's iterated. And this leads to an autonomous behavior of an LLM agent. So the main difference from an LLM and an LLM agent is the fact that it's iterative as opposed to be a one prompt, one response type of interaction, the ability to interact with tools, and also the fact that the agent keeps a memory of what it has done and of the interaction with the user. And a very interesting example, even I think in digital humanities, agents they still have to take off, but there is a quite recent paper, if you're interested in the topic, on an agent basically for data analysis of data coming from cadastres, so data about the city of Venice in the 19th century. So an agent that, given a question by the user, goes into these databases, looks for the information it needs, and also generates the code that produces analysis and visualization of data. So you have the title there if you want to check out the paper. In the remaining time, I will briefly touch upon what we're doing in GRAPHIA about LLMs and the infrastructure that we are setting up. One main bit of work we are currently doing is to adapt these models to the SSH domain. The reason for adapting is that when you change domain, the models often, they lack a specialized vocabulary, they lack a kind of a domain-specific type of reasoning, and also there is a factual gap. So there will be some details and facts that the model doesn't have access to. And for this, we have been putting together a corpus that can be used for this adaptation of large language models, which is called continuous pre-training, that basically updates and patches in a smart way without requiring too much computing resources, an existing model in order to provide a domain-adapted version of it. And this, again, I will make sure that there is a link in the slides when I share them. If you're interested, the dataset, the first version is already on Hugging Face. Has been created by GoTriple, which is a multilingual discovery platform, and you can check it out. I will skip this slide because I think I will digress otherwise, but I would really like to show at least 2 examples of things that use LLMs in Graphia. So the first one, it's the GoTriple chatbot, which is behind the scenes is using one of the models we have in Graphia, an instance of the DeepSeek model. And what it's doing is actually similar to what Notebook LM does, but for SSH publication. So behind the scenes, there is also a RAG application whereby you can create a collection of documents that are loaded into the RAG and then use the chatbot to explore this collection of documents. So for example, you can ask it to summarize the documents or to extract bibliographic references for them, so that if you go to the GoTriple platform, that's currently a beta feature you have there. And since recently it has been moved from an OpenAI model to our DeepSeek. And as you can see, there is these excerpts of the sources, and this already tells you there is a RAG application behind. The second thing that I wanted briefly to mention is that we are also doing this benchmarking of models. For example, one of the tasks on which we have been benchmarking them is the extraction of bibliographic references. The extraction and the segmentation of bibliographic references. Without going into much details, we have taken different models of different sizes, also fine-tuning them, so adapting them to our specific type of data, tested them against different tasks, and also comparing them with existing state-of-the-art tools, like, for example, Dropit, and then getting some insights, for example, about how well small large language models perform where they are untrained with some data for this specific task. And the answer is that they quite bridge the gap with the bigger frontier models. In the last minute or so, I also wanted to take the opportunity to say a few words about the infrastructure on which we are running these models, which comes from the Potsdam Supercomputing Center in Poland, where they're providing to our project quite a lot of very expensive and very powerful GPUs. Basically, all the applications that we have in Graphia, they run, and also the models, they run on their infrastructure. The platform, that is the LLM Gateway, that you find at this address, and that's basically what you have seen before. This interface here, it's part of the gateway. So this is how in the project we are the platform we have in the project for for authenticating and also having access to the different models. Until now, we have given access only to a few partners because we are testing it, but with today, we are opening it up to basically all the partners in the Graphia project. So if you want to have, if you want to receive a link to register for this and then get access to the to our models, just send an email to graphia@odoma.ch explaining to which models, if you know already, you want to get access, and also what you want to use them for, whether it's for experimenting or in a production application, and you receive a link that allows you to access them. If you are a partner, member of a partner in the GRAPHIA project, you will also have access to Confluence, where you will find the documentation, some documentation about this. And some interesting links from there are, for example, the Model Hub, where you can see the available models and also their status, their healthy status, whether they're working or not. You will have access also to the kind of uptime monitoring, where you can see whether there is, for example, maintenance planned or an incident. So there is a downtime of the infrastructure, which happens very rarely, as you can see from the over 98%, 99% uptime. And then you also have some guidance about how to set up, how to connect with these different models, how to create a new key, how to use it in the playground, which is what I showed before. It's this interface here, where you can play, you can select one of the different models, and then you can already ask questions for it, or you can also go for a bit more sophisticated access using notebooks and then using directly the Open API to call these models. Or you can also use some external tools like Misty, which also provides Reg, by the way, or Open Web UI, where you can just insert your key and use them. And if you are in GRAPHIA, there is a Mattermost channel called LLM4SSH, where you can get support and updates about what we are up with when it comes to LLMs in GRAPHIA. And that was it for the webinar. So looking forward if you have any questions.
Thank you, Matteo. That was super interesting. I will stop the recording now.